Hi, good morning. It's 12 o'clock, and my name is Henry Gunway, past chair of the AUE, and now your executive nominee for learning and development. This morning I will be hosting this event, supported by your vision team. Before the introductions to our speaker, Laura Bishop, I'd like to cover up a couple of ground rules. I'd like to encourage all delegates to post questions on the Q&A, and also use the chat function as we go, if there's any which is obviously burning. This will give me time to actually moderate. At the end of the session or the presentation, I'll facilitate the Q&A and ensure that all the questions raised are answered. Please note the event will be recorded and posted onto the AUE website and AUE Learning and Development for viewing for colleagues who are unable to attend. And at the end of the Q&A, I'll remind delegates that there's a networking chat roulette facility which will be open to allow members to be randomly paired to interact with other participants for 3 minutes. That's probably speed dating by any other name. This morning's session will be the role of heat pumps, which as they play an important role in terms of decarbonisation of heat in this sector. Our speaker is Laura Bishop. Laura is the Director of Infinitus Design and Chair of the Ground Source Heat Pump Association. Laura is part of this award-winning team, and also the Chair of the Ground Source Heat Pump Association. As you'll find out later, she's an accomplished presenter and has presented to many institutions and professional and trade associations. And further information on Infinitus Design and their service officer, which focuses solely on designing heat pump installations to help clients towards a net zero future. Do have a look at Laura's brand new website. It's really a joy to see. A couple of things about Laura, well-known facts. Laura has a master's degree in renewable energy systems technology, achieved through distance learning. So obviously, clearly she's no slouch, and obviously she's a skilled communicator. Little known fact, I've just found this out, Laura hails from Penn, beautifully described as the velvet end of Wolverhampton. Laura actually graduated with a BSc from Wolverhampton University in 2000, a university opportunity in the West Midlands, where, as you probably know, I was the Director of Estates many years ago, so therefore another coincidence. I'm delighted to hand over the proceedings to Laura, who has kindly offered to take questions during this session, if they are burning, but generally after the session, to be moderated. Here's them. Laura Bishop.
Thanks, Henry. And yeah, it is such a small world to find out that we both share a similar background at university. So yeah, thanks to AUE for inviting me to speak at this CPD session today on heat pumps. We're going to be looking at a few different aspects about heat pumps, bit of basics, bit of policy, and looking at, as it says there, plans for the future. So, and I'm really keen to get Q&A. So if you do have anything you'd like to ask, whether it's something I cover today or something you came along with that I don't cover, that's absolutely fine. Please do jot it down in the Q&A, and I will be definitely trying to go through that later on. So just a couple of bits of background. Henry's really ably and nicely introduced me there. So Infinitas Design, we're based in Derby, but we do projects all over the UK, and we are experts at designing commercial and industrial heat pump systems. So that tends to be the bigger side of things, and also multiple domestic sort of heat networks. So about me, a bit more about me. I'm a chartered mechanical engineer with the IMechE. I'm also a member of CPD and ASHRAE and several other brilliant institutions. We specialise, as I say, in renewable heating systems. We still do a bit of biomass, to be honest, but mainly we focus on heat pumps of all flavours, with or without heat and cool networks. As Henry says, I'm currently chair of the Ground Source Heat Pump Association, which represents installers, designers, drillers, and suppliers to the ground source industry. And I am an absolute and complete heat pump advocate, and regularly spend time talking to people about heat pumps because I think they're the best things since sliced bread. And hopefully I can pass some of that information on to you today. So, bit of an agenda, just 4 main items really we're going to cover. We're going to have a quick look at heat pump basics for those who might be new to the subject. We're going to have a look at the various ways that heat pumps can be applied, current policy and government strategy, things like that. And then we're going to have a look at the challenges and the opportunities for the future. So to start with then, let's just have a look at what is a heat pump. So heat pump is essentially, we're talking about vapor compression heat pumps at the moment, rather than any kind of other heat pump. They are the most popular ones used in Britain today. So we have 4 items in there. We have 2 heat exchangers called an evaporator and a condenser. The evaporator is the cold side, the condenser is the hot side. We have an expansion valve to allow refrigerant to expand, and we have a compressor, which is the electrical piece of kit in there. So basically the system works by heating and cooling refrigerant in its in a gas or a liquid form, to transfer energy from a cold source to a hot source. And when I say cold, we can take air, we can take water at minus 10, minus 20 and still produce hot water, basically, because of the amount of energy still available even at minus 10, minus 20, minus 30. And it converts that low grade free energy from water, from air, from ground, to high grade useful heating, hot water and cooling. So on the right hand side there, that's the back of a fridge. So if you have a fridge in your house, which obviously most people do, that is an example of a heat pump. So it's moving, in this case, moving heat from inside the fridge to outside the fridge to cool down the contents of the fridge. And we're doing the same thing with a heat pump. We're moving cold energy from outside into warm energy on the inside. That's essentially what we're doing, moving energy about. So if you have a fridge, that is basically a heat pump. So why are we talking about heat pumps right now in 2022? They have been around a very, very long time. The heat pump in its current form was founded in about 1946, and they have been deployed in the UK and across Europe for many, many years. In the UK, obviously, we have quite a heavy fossil fuel heating system, gas and oil and LPG. So why are we talking about heat pumps now? The Climate Change Committee states that around 31% of UK emissions arise from heating our buildings. That, you know, in other forms, some people say it's around 23, 25%. But what we all agree on is that the largest percentage of carbon emissions in the UK come from heat. So it's a greater carbon emission than transport, than electric generation, agriculture, all of those things. So it's the biggest area that we need to tackle if we're going to decarbonise our systems in the UK. So it's all about decarbonising heat, meeting our legally binding net zero targets by electrifying the heat that we generate. So rather than combusting a fossil fuel like gas or oil or coal, we're actually generating heat by by compression, so by electricity. The byproduct of that is clean air, because we're not burning anything locally. So of course we're going to have a look at the way electricity is generated, but we're no longer, say you've got a row of houses that are all burning gas or all burning oil, we're no longer doing that. So therefore we benefit from local clean air. And they are extremely flexible, and I hope that's something I get across to everybody today. What about heat pumps for net zero? So this is a quick look at why moving across from, for example, a gas boiler, which around 85% of homes in England are using natural gas to produce their heating and hot water. This table and this chart show why heat pumps can help us as we head towards a net zero future. So we have in the top row here, I don't know if you can see my cursor actually, but we have this is quite a small house, an annual heat demand of 5,000 kilowatt hours. So that's the heat demand that this particular building needs. If you're using a gas boiler at 93% efficiency, like a seasonal efficiency this is, the carbon emissions per year from that, using today's or 2021 government figures, is about 983 kilograms. If you move across to a heat pump, which is using electricity to generate that same amount of heat, your efficiency is higher than 100%. So we call it a coefficient of performance, of COP. If you're using an air source heat pump over the course of a year, because of cold outdoor temperatures in the winter when you need most heat, the COP or efficiency of the heat pump tends to be a bit lower. So using a COP of 2.9 or efficiency of 290%, the carbon emissions from that unit are about 362 kilograms per year. As you move across to ground source, which tends to have higher COPs because the temperature you're bringing into the heat pump is higher because it's coming from the ground rather than the air, your carbon emissions start to reduce even further. So from a baseline of gas, 983 kilograms per year, you can see on that bottom line there that straight away moving to an air source, you're saving about 63% of carbon emissions per year, and a ground source heat pump with a good COP of 4.5, about 3/4 of the carbon emissions from this particular building can be saved by using a heat pump. And that's just shown here in this little graph at the bottom. So you can see the gas boiler has quite a high carbon footprint, but the heat pumps have much lower carbon footprints. And it's projected that the grid, National Grid, will continue to decarbonise over years. So this is a BEIS, the Department of Business, Energy Industrial Strategy. This is one of their predictions for the way in which the National Grid will decarbonise in the coming years. So here we're around, it's about 183, oh, it's just here, sorry, at the bottom. So 210 grams of CO2 per kilowatt hour at the moment, but by the time we get to about 2030, it should be down at around 100 grams of CO2 per kilowatt hour generated. Just had a quick look at this app. I don't know if anybody's aware of this. There is an app that you can get called the Grid Carbon Intensity, and it means that at any point in the day you can log on and you can see just how carbon intense our national grid is. So this morning at 9 o'clock I logged on, and grid carbon intensity is at 250 grams of CO2. You can see that just over half of our electricity was being generated by natural gas this morning. Now, we have had times in the past where that has dropped right down to about 40 or 50 grams of CO2, and I think actually it's been much lower than that. You'll see that on particularly sunny days and particularly windy days. Today is a dull day, not particularly windy in Derby, so we are going to be reliant much more on gas, but that fluctuates on a daily basis. Really interesting actually to have a look and see how that's changing on a daily basis. So that's why heat pumps for net zero. Please do continue to ask any questions, because I know I'm going quite quickly, so I've only got about 45 minutes to speak, so if anything comes up, please do ask the question. So let's have a look at some of the ranges and applications for heat pumps. So here's just a few photographs of typical heat pumps that we'd see. So on the left hand side we have a ground source heat pump, actually two ground source heat pumps, 80 kilowatt system that is delivering heating and hot water to two rather large properties in a small plant room. The middle picture there is an 800 kilowatt water source heat pump system in a purpose-built plant room, and that's for a large college with 5 separate large buildings and a heat network. That's been operating since 2017. And then on the right hand side is something that are going to become more popular and more prevalent on our streets. That's a small valent air source heat pump, about 8 to 12 kilowatts. So that typically will be sitting outside somebody's house generating their heating and hot water. So you can see there's a wide range, everything from very small air source up to very large water and ground source, and actually you can get very large air source systems as well. They're flexible, as I said at the start, so you can have everything, as I've just said, all the way from little tiny units up to huge 10 megawatt plus systems that are running entire cities. They can use a very wide range of resources. So we've got the air, which is almost unlimited. We've got water source, that could be canals, rivers, the sea or lakes. We've got the ground, and that could be a closed loop borehole system. It could be a closed loop horizontal array. It could be open loop ground as well, using aquifers. We can have wastewater, so extracting water heat from sewage. We can have mine water heat recovery projects, waste heat from air systems. So there's a real range of things, and we can combine a lot of these as well. You can get high and low temperature heat pumps. Traditionally, heat pumps are generating temperatures of around 50 degrees C, and they certainly work more efficiently the lower you go. But you can buy now propane heat pumps, ammonia heat pumps that will do 80, 90, 95 degrees C flow temperatures. They can obviously do heating and cooling because they are essentially chillers working in reverse. You can have the same machine producing heating and cooling, so no longer any need to have a chiller on the roof and a gas boiler in the basement. They're really suitable for both new build and retrofit, and I'm going to talk a bit more about retrofit in a bit. And they are available for use on individual houses, multiple houses, offices, leisure centres, schools, hospitals, any kind of building that requires heating and or cooling, heat pumps can be used. And they're great for both 4th and 5th generation heat networks, which I'm going to talk about in a second. So they are really flexible and they can be used in all sorts of different locations and different applications. So just a couple of case studies. This is a system that was designed back in about 2018 and is now up and running. This is an estate village in Oxfordshire. If anybody's been to any of my talks before, you might have seen this case study before, but it's one that we're continuing to work on, really interesting project. As I say, rural Oxfordshire, off the gas grid, we had 26 homes that were using oil and LPG and electric, and in some cases actually not heated at all, and as a result they had really poor energy performance certificates. So the landlord decided that they were going to do something about that. They did some fabric upgrades, but the main project here was to install a 260 kilowatt closed loop horizontal array ground source heat pump system, delivering heat into a heat network to provide heating and hot water to these 26 homes. So in the middle of this drawing here, we've got a red box. That is the energy centre, which is actually here in the photograph on the left. And that's got 6 60 kilowatt NEBI heat pumps and some thermal stores in there. That's then delivering into 3 separate heat network branches, which is serving the variety of homes, and each home has a heat interface unit and HIU delivering heating and hot water. So in these photos you can see the type of houses. They're not new builds in any way, they're over 100 years old, each of these houses. And in the top right you can see the field where the closed loop horizontal array is located. So you can see that the field has been reinstated, it's now grass, you can't tell there's anything there, all you can see is these manifold chambers here. So when people say, can we farm the field afterwards? Can we reuse the field? The answer is yes, and there is an example of what it should look like after it's finished. So the tenants are now benefiting from clean heat, no more fuel and LPG deliveries, and they've not had their heat price increased at all as a result of going over to this heat pump system. And the things that we're now looking at doing with them is some of the private homeowners in the village are looking to connect on. So the energy centre was actually oversized to start with, and the the ground collector was oversized to allow more people to connect on. So that's something we're looking at. We're also looking at connecting up a solar array that they've got nearby to be able to offset some electricity running costs of the heat pump. We're also looking at increased thermal storage so that we can do some demand shifting. But what's really interesting is we visited here in February this year, or January, and we walked into the houses. None of them have had radiator upgrades, apart from where there was no radiators. And the houses were very warm, and the tenants are reporting that they are very happy, very comfortable with the warmth, even with no upgrades on their radiators. And then the second one is at the other end of the scale, which is an 8.8 megawatt thermal water source heat pump. This is for a Hall Hunter partnership, and EBTEC were the company that designed and installed this, one of our members. It's a leading soft fruit grower, and they deliver to Marks and Spencer's, strawberry crops in this instance. So this one is taking about 640 litres a second of water from the River Loddon, and you can see in the photos on the right the intake chambers for that, and the 3D model of the heat pumps at the top. So it's very industrial. It's got a heat main on site of around 160 kilometres, including the heat distribution pipework in the greenhouses. And in the first 6 weeks of operation, they generated 5,000 megawatts of heat, and they will save around 44,000 tonnes of carbon over 20 years. They've also got plans. I don't know whether this has actually happened because these things are slow burn, but installing a further 8 megawatts of heating onwards because they're so happy with the way this has been installed. And this is just one example of many kinds of this example, particularly in the rural environment, poultry farms, dairy farms and soft fruit growers are using heat pumps more and more, especially as oil prices increase. So what about hard to heat buildings, which is where Infinitas spends a lot of our time designing heat pumps. So there's loads of examples of heat pumps in hard to heat buildings, and hard to heat buildings is really any building that exists already. That I think there is a big myth about heat pumps not being suitable for existing buildings. We have millions of existing buildings, and if we're unable to put heat pumps into them, we've got a problem. But the reality is that if you're working in the industry, we have lots and lots of examples where heat pumps are working very, very well in existing buildings without needing to rip up floors, take out radiators, clad the building to within an inch of its life. National Trusts are actually using heat pumps in several of their stately homes, and they cannot do any fabric upgrades, but they're still working very well with heat pumps. Of course, Fabric First is recommended. The reason for that is because it can reduce your peak demand, which means that your heat pump or even your gas boiler has to be smaller, and your annual heat demand will be reduced, which means that you are generating less carbon and it's costing you less to run. So if you can do Fabric First, you absolutely should. But if you can't, as with the National Trust, it's not a showstopper. But you do need to have good design at the start of the project, and you need to take a holistic approach to the project. It's not just take the gas boiler out, put the heat pump in. It's a whole, what does the entire building need? Do you need to replace radiators? Do you need to replace air handlers? Looking at the system as a whole, and then you can decide as a good design engineer whether you can just put the heat pump in and everything will be fine, or whether you can put the heat pump in and you need to make some other amendments to make the system work well. Another thing with hard to heat buildings or existing buildings is to operate the heat pump in a different way. So here I've put low and slow. So a gas boiler typically will come on with a big boost in the morning, warm the building up very quickly, and maybe peter off during the day, and then there'll be a second boost around 4 o'clock-ish, something like that. Don't do that with a heat pump. Best thing to do is to leave it running all the time in the background. With these older buildings, thermal mass helps because it keeps the heat in within the thermal mass. So operating low and slow is the way to go, particularly in existing buildings. You do have options with high temperature heat pumps. As I said, you know, propane and ammonia, they can go much higher. You will get hit on the efficiency, but if you don't have a choice and you want to de-risk, high temperature heat pumps is the way to go. And obviously you've also got hybrid or bivalent systems as an option. So maybe you keep your gas boilers as a backup and they come on when it's extremely cold outside, but your heat pump picks up 99% of the load for the rest of the year. So definitely looking at different kinds of options. And this is a job I recently visited down in Cheshire, I think. So this is a grade 1 listed home where someone's just moved in, you know, businessman with his family moved in. No fabric improvements at all. They've got 2 heat pumps running here using the lake. And this is a typical radiator that they're using at the bottom. And when we walked in, this was actually February this year, not really cold outside, but it's around 3 or 4 degrees outside. The house is beautifully warm, and the guy who lives there says I have to actually take my jumper off when I come in because it's warm. Just proof that although there's lots of myths around heat pumps not working properly in our buildings, there actually are, in reality, lots and lots of examples of them working well. So let's have a look at some government policy and where we are with what the government is saying and doing. So going back to November 2020, Boris Johnson announced the Green Industrial Revolution and the 10-point plan. And that instantly started conversation around heat pumps. So we really saw a step change when Boris came out and said that. And love him or hate him, that has kick-started this new focus on heat pumps. Unfortunately, that sort of coincided with the renewable heat incentive ending. So it was initially due to end in 2021. Then there was an extension for a year due to COVID. The domestic RHI has now actually ended, and the non-domestic RHI is continuing to run out to April, so March next year. In April this year, or actually in May, because it was delayed, the boiler upgrade scheme, the BUS, was released, and this is a grant scheme for homeowners. You get £5,000 to install an air source heat pump or £6,000 for a ground source heat pump. Remains to be seen how well that will run out, but we're keeping a close eye on that. And on the commercial side, there's a public sector decarbonisation scheme. We're about to go into round 4 of this, where money is released for the public sector to decarbonise their buildings such as schools, libraries, museums, council buildings. But unfortunately, there isn't actually any support now for just standard commercial buildings, offices, factories and things like that, which we think is a major, well, we're still seeing projects coming through, but it's unfortunate that the government haven't seen fit to provide any support for that area. However, we did get the heat and building strategy last year, November last year, and on the back of that there were some consultations on off-gas properties, which means those not connected to the natural gas grid. So it's on oil and LPG and coal, and the consultation proposed that in 2024 all large buildings greater than 1,000 metres squared will not be able to buy a new fossil fuel boiler after 2024, and in 2026 everything else that's off gas will not be able to buy a new boiler. It doesn't mean they'll come and rip out boilers, but when it comes to replace them you won't be able to buy a new boiler. And the point is that the government has specifically said they want this to be a heat pump first approach. So we're waiting for the results of the consultation. That's not been released yet. Those were the proposals. Everybody got a chance to have their say on that consultation, and we're now just waiting to find out whether that's something the government will put into force. If they do, we had the carrot with the renewable heat incentive. This is now the stick. So yeah, we need to actually make people aware of this, because it will obviously come as a shock to a lot of people that are not on the gas grid, and make them aware of what their options are, and make it easy for them as well to come over to heat pumps, because as we'll come on to later, some of the challenges are around awareness of heat pumps. So what sort of innovation are we looking at with heat pumps particularly? One of the things that the government is particularly focusing on, and rightly so, is reducing the capital costs, because that is a major challenge for heat pumps, especially when looking at the alternatives. Shared ground loops is a big innovation that is in some areas of the country almost becoming standard. Other areas it's not so. This is where you have a central borehole system that then makes a low temperature heat network that's serving multiple houses or all kinds of different buildings who then have their own ground source heat pumps. I was going to talk about that, but time isn't going to allow me. So if there's time at the end, I can talk a bit more about that. Flexible heat tariffs, they are going to be extremely important as we move more towards electrification of heat. Thermal and battery storage, and linked in with that is demand side response, so that you can generate heat when tariffs are favourable, or when you're generating solar electricity and electricity becomes free. And then your demand side, which is your house, can then take, or your building can take heat out of your battery or out of your thermal store, rather than taking it directly from the heat pump. That can also help to balance the national grid, by the way, and there are revenue streams around that. A move towards low global warming potential refrigerants. So there is the F-gas refrigeration gas phase out happening. So a lot of heat pumps and manufacturers are now moving across to things like propane, carbon dioxide, ammonia I've talked about, and this sort of synthetic refrigerant R1234ZE. The good thing about those is also they are able to do higher temperatures, and some of them have zero global warming potential, particularly in the natural refrigerants. So we are seeing a move to that. Higher temperatures, higher COPs. So those are the innovations that are coming along or are happening right now, and we're going to see more of that. But what about the challenges? So this is the last bit of the presentation, the challenges and the opportunities. So one of the main challenges which GSHPA and others like Electrify Heat and Energy Networks Authority and people like that are working on is the running costs of heat pumps, the capital costs we've just talked about. Skills and training is a huge area problem, not just in England, not just in the UK, but across Europe. And then finally, the myths, which for me is one of the biggest problems we have in the UK about making the switch to heat pumps. So the first thing is looking at running costs. If we go back to the table we looked at the start, we had a building with an annual heat demand of 5,000 kilowatt hours a year. If we take the same building and look at actually what the running cost of that same building using gas boiler, heat pumps, and I've also here included oil boilers and direct electric heating as well, so you can see the difference in costs. And at the bottom, obviously right now, because prices are fluctuating all the time, everybody's on a different gas price and a different electricity price. It's all over the place, going up and down all over the place. I've just picked gas at 8p a kilowatt hour. Fuel oil today, according to Boiler Juice, is about 8.56p, and I've just picked electricity at 25p a kilowatt hour. I know some people are actually now paying about 30 to 35p. So if you take these different types of heat generators to deliver 5,000 kilowatt hours a year, you can see in the graph at the bottom that costs, the highest cost is on the oil boiler. Oh, sorry, no, that's wrong, isn't it? It's because I added in direct electric afterwards. So the actual highest cost, the highest running cost is on the direct electric heating system, £1,250 a year. And that's because it's 100% efficient. So your electricity price is 1 unit of electric equals 1 unit of heat, and electricity is expensive. In the UK, we actually have the worst spark gap in Europe, which means that we have the lowest gas price and the highest electricity price, the biggest gap between the two. Other countries, it's switched the other way around, or the gap is not so different. So when you're looking to switch from, say, a gas boiler, which in this case is costing £430 a year to run, if you're looking to move across to a heat pump, you could be looking at equivalent cost, or actually sometimes it can cost you more. But because of the fluctuating gas and electric price, we're actually seeing that change now. So that's quite a recent change. So fuel oil boiler costs about £460 a year. The air source is £446 a year. But if you start to look at your ground source heat pumps with good COPs, you can actually make decent savings on your annual running cost based on natural gas. I apologise that the graph is not the right graph. So the ground source heat pump offers the highest efficiency and the greatest carbon savings. However, it's the most expensive one to buy. As we look at the next slide, you're looking at about £25,000 a year. Sorry, £25,000 to have a ground source heat pump installed. It's very variable cost, but that's around the average. But direct electric, although it's the cheapest to fit, and I think this is what we'll probably see as people move away from gas, is they'll go and put electric radiators in. They're cheap to buy, but they are very expensive to run. And if you're looking at, say, 10, 15-year running costs, direct electric is going to hit you over that period of time. So the conclusion is that ground source saves the most carbon. It's the cheapest to run right now with a good COP, but it's also the most expensive. So if we move on to the next challenge, capital cost, if you were to have a new fossil fuel boiler in your home, I mean, obviously this depends on the size of your home, but you could be looking at around £3,000 for just the boiler fitting, buying the boiler and getting it fitted. But a new air source heat pump will cost you £8,000 to £10,000, and a new ground source could cost you £20,000 to £30,000. So the problem we have is that for net zero and achieving net zero and decarbonising, we need to go to heat pumps because of that big carbon saving that it gives you straight away. But unfortunately, they are the most expensive to buy. So this is the reason that the government actually brought out the boiler upgrade scheme, but that's very much focused on air source rather than ground source. £5,000 grant means that you're only spending £5,000 on your air source, which is not much more than your new gas or oil boiler would cost. So unfortunately, that means that we still need grants and subsidies. I'm not a fan of grants and subsidies. If we were to move environmental levies off the electricity price and put them onto gas, where they have historically sat, we would be in quite a different position. And it's something that a lot of us in this industry are lobbying for. And I'll talk about that more at the end and the opportunities. So third challenge, how are we doing for time? Okay. Third challenge is not one that is limited just to heat pumps. Skills training and awareness is a general problem across engineering and the construction industry. And if anybody here is working in engineering of any type or construction, you will know that this is an acute problem. Competence of people, so competence of installers, designers, maintainers, suppliers, and also the compliance with regs and compliance with specifications, but even the ability to get people in the first place. I mean, I tried to recruit for my business, and it's basically impossible, which is really sad. So it'd be good to train, and there's a huge opportunity obviously there for new people coming into the industry. So that's the flip side, is the opportunity there. But unfortunately, because we've had this lack of investment in renewables for such a long time in the UK, unlike Europe, obviously employers are not going to train up and recruit renewables engineers because they haven't got the work for them. Gas is still huge and oil boilers are still huge, so you've still got a lot of people just installing and maintaining gas and oil boilers, and we need them to come across and start to take up some of these training courses that are now flooding onto the market. Definitely a lack of focus on design in our industry. In heat pumps particularly, I had a conversation, one of my people that I've worked with before did a very large museum up in the northeast and had asked me to design a plant room for them. I didn't hear anything from them, and they said in the end they just muddled through. And this is a very large heating and cooling project for a museum, and to hear them say that they've muddled through, that means it's not going to work, basically, because they don't think that design is important, and it is absolutely critical, particularly in the larger projects. So that is a problem in our industry. Of course, poor installations means you are going to get poor performance, which means you're going to either have a system that doesn't work or it's going to cost you an arm and a leg, and that always results in poor PR for heat pumps. So you always hear about the bad installs, you don't hear about the good installs. And I can see actually with the boiler upgrade scheme and more people installing air source heat pumps in houses, we can already see that causing a lot more of these headlines of heat pumps don't work, which is really bad, and we are trying to do everything we can to prevent that. But all behind that is this continuing lack of government direction and strategy. So we had the heat and building strategy back in November. It wasn't very specific about how we're going to do what needs to be done. And then the latest energy announcement, which was back in February or March, didn't talk about heat pumps or energy efficiency at all. It talked about nuclear power and wind, which of course we need to decarbonise the grid. But once again, we are lacking this direction and strategy from the government, which underpins everything we're trying to achieve. So we do need them on board and doing things right and opening the way for us to go forward with the heat side of things. And finally, the lovely myths. Here are 3 headlines from March this year, one from the Telegraph, one from the Mail Online, and one I think from the Guardian. This was, I think. So we have expensive and wasteful heat pumps, not the solution to Britain's energy crisis. Heat pumps are one of the biggest cons I've seen, and Boris's grants to install them is doomed to fail. And 6 reasons not to buy a heat pump in 2022. And the problem with this is that these are splashed across the front of papers with usually very little technical input and written by people who don't seem to know much about heat pumps at all, but the people reading it also don't know about heat pumps, and this unfortunately is the message that they are given. We are again trying very hard to myth bust as often as we can and to engage with journalists to tell them, come and speak to us before you go and blab these things out, because it's not doing us any favours. However, this photograph here, I thought I'd include this because this is the reality of what can go wrong. Expensive and wasteful, biggest cons, and not reasons not to buy a heat pump. This is somebody's patio that was previously flat. Somebody has installed some kind of borehole or something underneath the patio to do a ground source heat pump. Not big enough ground array, the ground is frozen, and this is the result. This is what happens when things go wrong. So you have actual physical problems from not installing and not designing ground source heat pump systems correctly. So I can totally see why these myths and why these problems arise. And as an industry, we've got to get better at doing good installs and talking about them. But unfortunately, the media is not helping us at all. And I've actually sent them messages to come and talk to me about why they've done that, but I don't hear anything back. So there we go. So to finish on a positive, the opportunity. So interest in heat pumps is certainly not going away. There's loads of opportunity for good design. So this is also a good opportunity for recruitment, for training as well, for becoming a new, entering into the market. There's a huge demand for engineers, for installers, for construction people, to get into this. Another big opportunity around green finance, and it's something that's been talked about a lot. So leveraging finance to make it possible for people to have heat pumps without paying for them. So investment, pension funds, things like that, investing into the infrastructure of ground source heat pumps. Talk very briefly around this flexibility and time of use tariffs. Octopus, for example, do a time of use tariff so that when there is a surplus of electricity on the grid, you can switch your heat pump on remotely and take advantage of lower electricity tariffs. And if you're using thermal storage, again, as I said before, you can run your heat pump when it's cheap to run, even if there's no heat demand, and then you can take your heat demand off your thermal store or run your heat pump off a battery. So many different ways of reducing your running costs by employing flexibility. One thing we're really lobbying government on right now is an electricity tariff specific for heat pumps. So if you have a heat pump with an electricity meter, you can pay a much reduced tariff, and that would then help people really to move across to using a heat pump, because if you can say have an electricity tariff of 10 pence a kilowatt hour just for your heat pump, similar to your electric vehicle, although of course running an electric vehicle is cheaper than buying diesel right now. It's the other way around for heat pumps. It's cheaper to run a gas boiler than it is to run a heat pump, especially if you're paying 35 pence a kilowatt hour for electricity. Thermal storage, demand side response, using thermal storage to peak shave, so not sizing your heat pump too big and using your thermal storage cleverly to chop off any peak demands. That's particularly important in commercial systems. Heating and cooling, there's going to be a lot more demand for cooling as the planet warms up. It's the unfortunate side effect of global warming. We will need a lot more cooling in the UK, and already we're seeing these big posh houses particularly having heat pumps that can do heat and cool, cooling in the summer, heating in the winter, which is perfectly possible with heat pumps that are available right now. And heat networks, whether that's a shared ground loop system with individual heat pumps in individual buildings, or whether a bit like the North Aston estate that I showed earlier, central heat pumps delivering heat into a heat network, they will become more prevalent. And as I say, in some areas of the country, for example in Cornwall or some of the off-gas villages, they are starting to become more widespread. And if you are interested in training, either being trained or becoming a trainer, obviously there's huge opportunities around there as well to transfer knowledge and mentoring and things like that. The GSHPA is about to launch a training course for consultant engineers and architects on ground source heat pumps specifically. It's a 16-week training course, and we're going to be following that up with some domestic-led training courses as well, which will be in the classroom as well as online. And that's really important, getting that practical hands-on experience as well. So I think that's I've talked quite a lot. So that is the end of my presentation. So thank you for listening. And if you've got any questions at all, I'm really happy to take them now.
Okay, thanks very much, Laura. Thanks for the first question was from Paul Eccleshaw. And his question was about consultancy design costs for air source heat pumps to replace boilers. And he's obviously very keen to actually understand that air source heat pumps that you've rightly pointed out cost more for the design than also for gas boiler replacements, and there's more capital costs. Do you think, what he wants to know, do you think the cost of heat pumps will actually reduce over time? So obviously the demand and production gets to a higher volume.
Yeah, so I think I think there's two parts of the question, isn't there? So there's the consultancy costs of designing a heat pump system, a heat pump plant room versus a standard gas boiler plant room. But I think to come back on that, I go into lots and lots of plant rooms and I see terrible design practice in gas boiler plant rooms. So I think actually there's a lot left to be desired on consultants or designers not designing plant rooms correctly, full stop, regardless of whether they're boilers or not. So actually I think there should be more money spent on designing a gas plant room, and that should be actually be the same for a heat pump, because a heat pump and a gas boiler both generate hot water. That's what they do. That's all they're doing. Or sorry, if it's a heat pump, might also be doing cooling. The hydraulic side of things is exactly the same. Delta T's, flow rates, pipe sizing pumps. and then heat emitters, sizing your heat emitters. So actually the consultancy cost for designing a plant room should not be different between a heat pump and a boiler. It should be the same. It's just that you need to know probably more what you're doing with the heat pump because it's lower flow temperature, but that's all it is. It's just a lower flow temperature. But will the cost come down? And I should also say actually that there is software out there that should definitely be used for using it when you're going for a heat pump, especially if you're retrofitting one. That software like HiSopt, which will do your hydraulic modelling, and you can do your what if analyses, turning down temperatures, changing delta T's, changing pump speeds and things like that. So I'd recommend that whether you're doing a gas boiler or a heat pump, to be honest. The cost, as we get people better at designing, the cost should come down purely because it will be quicker. So for example, when we design a plant room, we're not starting from scratch every time. We've done loads and loads of plant rooms. So therefore, there's always going to be the survey cost, and there's always going to be the investigative costs. But the actual design, you might have 50% of a design already that you can then lift and use again. So the cost should come down the more familiar people get with using heat pumps, and also because you'll build up a library of designs that can be reused.
Actually, the question that Paul's actually asked, I actually don't really understand why the design cost for a consultant, Paul's actually put it at 2.5 times the cost of the design of a standard boiler replacement. I don't really understand why the cost was higher.
Yeah, that's I think probably, as I say, it's because I think there is, with gas boilers, there's less risk of things going wrong. So it's high temperature, and if it's inefficient, then it doesn't matter because gas is cheap. That's what we see. That's what I see personally. And as I say, I go into a lot of plant rooms that have been designed absolutely terribly on gas boilers. So the same design philosophy and the same design time should be spent on designing gas boilers as it should be on any heat pump system. And as I say, that all they're doing is generating heated water.
I mean, I can actually see the question if it was a ground source heat pump and there was more to do with boreholes, hydrology, and obviously and check to make sure that the ground was right, etc. But air source heat pumps, I can't. I think I'd probably challenge that design cost myself personally.
And I think, well, yeah, you're right. If we were talking about on the ground source side, yes, there is a whole other cost part, which is the ground side, the investigations, the design, the thermal response testing, things like that. Yes, that can really mount up. What I would say on that though is the increased efficiency of ground source, and also the chance to decouple the cost of the ground array as an investment does help ground source up. But yeah, the design side of ground source is more expensive.
Well, I'll probably answer this question myself actually. I was just thinking about it. In terms of there probably is a little bit more work because they probably will need to actually consider the electrical power infrastructure requirements because obviously some of the large installations, some of the cable sizes will not be right. They may actually have to contact the DNO as well.
You will have to contact the DNO. That's what actually if you're doing a feasibility study on a heat pump, that's one of the things you do have to bear in mind is contacting the DNO as soon as possible, because you might find that you're grid constrained in that particular area, and therefore you can't have a heat pump because or you might have to spend £250,000 on an electrical upgrade. That's something the ENA are very, very aware of. And are working with people like GSHPA to make sure that that's not a showstopper for projects.
So, bearing that in mind, can you actually sort of give us some insight on the testing and commissioning processes of bringing a ground source heat pump online or an air source heat pump online, and also how that relates to the DNO? Because the DNO can be a showstopper, can't they?
Yeah, so before you get anywhere near placing orders for heat pumps, you will have already talked to the DNO, and they will have already confirmed that you've got sufficient capacity, no problem, or B, you need to upgrade 100 kVA or you need a new transformer or something like that, and that will then have been factored into your cost model And if the project still works financially, then you can go ahead and get that done. So that work has to be done probably up front, sometimes concurrently with the rest of the install, but that would be well before. So then you'd have your it would just be the same way as just commissioning a gas boiler from then on, except that you're essentially plugging it into the mains. But you would have already got the cables all correctly sized and brought in to the energy centre or the plant room.
That's great. There's a question here from Tim Coots. Would you use a heat pump for a district heating network?
Yes.
You're actually going to talk a bit about fourth generation and fifth generation district heat networks.
Yeah. So I had to take that out because I thought, am I going to run out of time? But we have got a little bit of time now. So fourth generation networks, similar to the North Aston case study I showed. Anything networked together. So even if you've got two houses connected to one heat pump, there's your heat network, and there are loads and loads of those. For example, on the non-domestic RHI, we've done a lot of systems where farmers might have 7 holiday lets so they put heat pumps in a barn and then run district heat network around the holiday lets, and they're all being served by that particular heat pump and taking RHI for that. So because you've got a lower flow temperature to start with, obviously your heat loss in your network is less. You can use your standard pre-insulated plastic pipework, so the costs can be less than using steel. So as we're looking forward to things like the Green Heat Network Fund, which was released a couple of months ago, which replaced the Heat Network Development Unit, HINDU, the government have again placed their hat in the ring for heat pumps, because the Green Heat Network Fund is specifically for heat pump led or low carbon led heat networks. So they want to get away from gas CHP and gas boilers. So that's where the funding is going to be, because it works. We've got the Clyde Bank high temperature heat pump system that went in last year, doing the network up there. We've got Swaff and Pryor down in Cambridgeshire, that's 300 houses going onto a central heat pump system. I think that's 2 megawatts, 1.5 megawatts of ground source and 500 kilowatts of air source with electric boiler backup. So this is going to happen. Fourth generation heat networks, no problem at all with heat pumps delivering heat. Fifth generation is the cold loop side. So that's where you might, as I said before, you might drill down boreholes and then circulate that water from the boreholes around a network, and each building has its own heat pump. And the benefit of that is that if you've got an older building that needs slightly higher temperatures, that can have one particular type of heat pump. If you've got another building that's brand new and it needs low temperatures, you can have a different heat pump. And each building takes just what they need, and they work particularly well where you've got cooling, because you can also benefit from free cooling via the ambient loop in the ground, or you can use the heat pump to chill that off further if you need specific cooling in the summer when the network is too high in temperature. So there's in South Bank University, they have a balanced energy network, the BEN system, which is shared ground loop, serving some of the buildings on campus there, heating and cooling, using heat pumps and using a 5th gen network. So they're already happening as well. We've got one actually that's just been commissioned over in Stoke. That's 25 old people's bungalows running on a shared ground loop. And each one has just got a tiny little 5 kilowatt ground source heat pump in the bungalow. So that's happening right now. And we will see more of those as Green Heat Network Fund money starts to be rolled out.
Laura, there's a joint question here from Tim Coots again, and also from Dave Bassett, and probably interested in how do you actually sort of deploy the BMS system to actually better control your heat pump in operation in terms of scheduling, energy tariffs, peak demand, storage, etc.
That's a really good question, and controls generally is absolutely critical part. And although we mechanical engineers and design engineers, finding them is like finding gold dust. Finding controls engineers is like platinum dust. But it's so important, and if we don't get the controls and the building management or heating management system right, things won't work properly, or they won't work efficiently. So if you're putting in a heat pump, say for example you've got a plant room with 1 megawatt of gas boilers in that's being run by a BMS, and you're going to put in 700 kilowatts of ground source heat pump, let's say. Very early on, a bit like with talking to the DNO early on, you must get the controls guys on board. You must understand how the BMS is working, what the control points are, how it's operating, what the time clocks are all doing. I mean, in my experience, actually, when I go into sites that have got BMS, most of the managers don't understand how the BMS is working, and some of them turn it on and off manually, which is not great. But I've yet to visit a site, and I've been to hundreds and hundreds of sites that has actually running their BMS correctly. But nevertheless, the heat pump itself will control itself, and it's a good idea to let it do that. You can use the BMS to turn it on and off as like on a time clock basis, but not to operate the heat pump. I wouldn't recommend that. Let the heat pump do its own thing using its own inbuilt temperature or pressure sensors, however you want to control it. And the heat pump will use to control its own brine temperatures as well. So pumping variable speed depending on what the heat pump is doing at any one time. But yes, incorporating the heat pump control system with the BMS is critical to success, to efficient running. And the earlier you can understand the way the BMS is working and the way your heat pump wants to work, and bring the two together into a new control strategy, the earlier you can do that, the better. And just make sure you've got enough control points when you're designing your heat pump system. Better to have too many temperature sensors than not enough and have to go and put them in afterwards. So I hope that answers the question.
Yeah, that's okay. You mentioned in your presentation about thermal storage, and obviously, can you just give some idea of size of thermal storage to actually provide sufficient buffer for systems to actually work?
Yeah. So some heat pumps will need a minimum volume on the condenser side. So that's really important to understand to start with, because that's your minimum thermal storage size. And of course, if you've got pipe work going into a heat network, that might give you enough volume. So you may not need a thermal store. You don't always need a thermal store with a heat pump. However, if you have any intentions of doing any demand side response, you will need thermal storage. And the volume of thermal storage will then be dependent on the thermal profile for your building. So if you've got a big peak in the winter or in the morning, then that will determine the size of your thermal store. Say, for example, you want to be able to turn your heat pump off for 3 hours between 4 and 7 in the afternoon, because that's your red period, and that's when electricity costs the most. You need to know how much energy is demanded in that 3 hour period. And there you need to make sure that your thermal store is available for that 3 hour period. So you need to really have a good understanding. Half-hourly gas consumption data or half-hourly heat demand data is really, really important to accurately size your thermal store. You can go the other end of the scale and just say, well, it's 20 litres a kilowatt. Job done. So yeah, I think when we're sizing thermal stores, we try to get a really good understanding of the thermal profile of a building on a half-hourly basis and size the thermal store accordingly, enable it to switch off for 3 hours or 5 hours or half an hour or whatever they want to do.
That's great. There's a statement from Paul Eccleshaw, sorry, to say that he's had 5 quotes. I don't know whether it's air source heat pumps or ground source, but they're all in the same range. One final question. You mentioned PSD4. As a warrior from PSD1 and 2, we want to know what you know about PSD4 and when do you think it's going to be notified and released?
All I can say is that PSD4 is on the table right now. That's what I heard yesterday. Now, I don't know what on the table means. It hasn't been released, and I don't know if there's any dates yet. Sorry. I should know. I need to find out for myself.
No, it's always tricky, isn't it, with PSD as funding, and all I can tell you, it's going to be a race for time. My experience is just a race for time. So you can imagine those little motorized cars, and it's going to be let go. It's a race for time, and it's first cross the post job.
That's why so many PSDS jobs have been air source, purely because of the timescale. So it's usually 1 year from winning the cash to actually getting the project finished. And to get a ground source heat pump job designed installed and commissioned in a year is nigh on impossible and will probably not work if it is done in a year. However, PSTS4, some of my colleagues at Heat Pump Federation have been working with Salix to ensure that it's actually a 2 to 3 year rollout rather than a 1 year. So what I do know is that PSTS4 next is unlikely to be a 1 year rollout.
Yeah, that's fine. I think we've probably come to 12:59, and we've probably come one final question from myself, really, in terms of ground source heat pumps. And obviously, you talked about actually having bores and also linear. Have you got any comments on geothermal ground source heat pumps with 200-meter loops?
Well, 200-meter loops is still ground source, so geothermal is more like 2 kilometers deep.
Right.
So a standard ground source heat pump system will borehole depths is anywhere between 100 and 300 meters. So that's still classed as surface ground source. Deep geothermal is really good. We're working with the British Geological Society at the moment on that, but of course it is limited to certain areas of the UK. We've just finished working on the Eden project, which is 5.5 kilometers deep, but they are so high risk. That's the only problem, because you've got to drill down and across and hope that you hit the seam you are aiming for. So they are brilliant because they're actually bringing water, steam to the surface, which they're going to use to generate electricity. So completely, you don't even need a heat pump there. You just take the heat and steam out the ground. But they are high risk and only available in certain areas of the UK.
Certainly not in mining areas.
Or mining, again, because you can access quite warm water. Mine water can be around 25 degrees. You can access that in many areas of the UK, but then you've got to get involved with the coal authority, who can be difficult.
I think we've exhausted all the questions. All that reminds me to say is thanks very much for the presentation. On the chat, there's lots and lots of thank yous from the sector to say thanks very much. It was all very interesting, and I quite enjoyed the presentation, which is a really good indicator, and I'm sure you'll be very pleased. So thanks very much, Laura. All that reminds me to say is that the next presentation is on the 6th of June. It's going to be Harper Adams' journey to carbon net zero and PV installations case study and battles with the DNO. It'll be led by myself, if I'm still alive, and the old group. So therefore the introductions are going to be really interesting. Thanks for your attendance today. I hope you found the whole event worthwhile. Do have a look at Infinitus's website. Please email with any feedback, good, bad, or indifferent. Enjoy the rest of the day and continue to register for the AUE CPD knowledge series. Thanks very much. Good afternoon.